let's continue to talk about non-determinism. So in the book, it's page 47, 49, and some pages following that, but it's section 1.2 in the book, which you should be reading. So non-determinism is a generalization of determinism, where instead of one next move, you're allowed multiple next moves. So classical computation takes you from a state to another state, basically. So it looks like a long sequence of state changes. Now, non-determinism allows you multiple next states. So basically, the computation gets from a linear list of states changes to a bifurcating tree. So it could be several next states and several next states for each one of the subsequent states. So the computation generalizes from a list to a tree. So just like a tree is a generalization of a list, or a list is a special case of a tree, determinism is a special case of non-determinism. In terms of the transition function type, instead of taking you from a state and a symbol to a new state, you go from a set of states and that same symbol to another set of states. So the type takes you from a member of the power set to a member of the power set, from a set to a set of states, as opposed to from a single state to a single other state. So the computation becomes a tree. So that raises some interesting question about acceptance. Does this computation accept or doesn't accept? Well, if it's a single long list and the last one is accepting, obviously it accepts. But now it's a tree, and there could be multiple accepting paths, and some paths could be not accepting. So the question is, when does it accept and when does it doesn't accept? So the definition that we use is that it accepts if and only if there exists a path to some accepting state, we're good enough. So that's the definition of non-deterministic acceptance, if there exists a path from the root. So you don't have to accept everywhere on every path. As long as there exists a path to some accepting state like this one, or some path to this one, or to this one, and that's where it ends, then the whole thing is said to be accepting. So this is a lot like in life, where you have, you know, in say finance, the venture capital model of, you know, capitalism, where venture capitalists might fund a bunch of different companies at the same time, like 20 companies, knowing that 18 or 19 of them will fail, but one will succeed, and one will become Google or Facebook, and that will pay for the other failures, and that's okay. So it's a good model of doing business. It's a hedging strategy. So this is the same kind of idea. It's a hedging strategy there too. You know, in other aspects of life, you know, same thing. If you apply for jobs, right? You don't apply for one job and then wait. You apply for 10 or even 20 different jobs, and 1 or 2 or 3 will, like, you know, accept your application and give you the job. The other 19 or 18 may not, and that's okay. No big shakes, right? So same thing here. As long as there's one path to success, you're good on non-deterministic acceptance. So let's look at an example of how this might work. So let's construct a non-deterministic finite automata that accepts all strings whose 7th symbol before the end of the string is a B. So here is this finite automata that's non-deterministic. How do we know it's non-deterministic? Because some transitions will go to multiple places. If you're in here and you see a B, you go back to yourself to Q0, but you also go to Q1 on the same transition, a B. Okay. So let's say we want to see if the input ABA, BBAA is accepted. And sure enough, the 7th character from the end, 1, 2, 3, 4, 5, 6, 7, is sure enough a B, and we want to accept this. Let's make sure that gets accepted here. So how does this work? You see the A, and so this transition gets triggered, and this gets triggered, and you go back to yourself, so you're in Q0. The highlighted green state is the state you're in right now. In this case, it's Q0 based on the A. Now you see a B. So Q0 and a B, this transition gets triggered, but so does this. See, I'm animating them, PowerPoint in action. And B will get you back to here, but B will also get you here. So now you're in these two states, Q0 and Q1, both. Now you see another A, the input read-write head goes forward. It's really a read head. It doesn't write anything. So the input read head goes forward. So this gets triggered on an A, and this gets triggered on an A. So you end up here and back to yourself. So now you're in state Q0 and Q2 simultaneously. Okay, you see another B. So a B here will trigger this transition, and it'll also trigger this transition and this transition as well. All 3 transitions will be triggered on a B. And so you'll end up in this state here, Q0, and this state here, Q1, and this state here, Q3. And so these 3 states are now active or highlighted, or you're in all 3 of them simultaneously, non-deterministically. Another B, it'll get you this transition, this transition, this transition, and that transition. 4 transitions get triggered now. And you end up in these respective states, you know, Q4, Q1, and Q0, all at the same time. and also Q2. Right? And then you see another A right here. Once you process this A, it gets you into here, into here, into here, and into here. 4 different transitions get triggered, and so you end up in states Q5, and in state Q3, and in state Q2, and also in state Q0 as well. So you're in 4 different states now. You see another A, right? And another A after that. It'll get you into these states, and finally, after the last A, you'll end up in Q7 and in a few other states. But Q7 is already accepting. Remember the definition: as long as you're in one accepting state, the whole thing is successful. So the string therefore gets accepted because this series of states, at least one of them is final. So there exists a path to a final state through all these transitions based on this input string. So this input string gets accepted by this non-deterministic finite automata, and it's good. It's in the language of the automata. And sure enough, the 7th symbol from the end was a B. Now, why does this machine work in general? Because as long as you see an A or a B, you end up in this state. But the minute you see a B, you also start a token down this path. So a B will get you into this state, and then an A or a B will keep getting you further down this line, either an A or a B. So once this gets entered via a single B, 1, 2, 3, 4, 5, 6 more transitions will activate the 7th state. How many can see that? And once the 7th state is activated, that means the 7th character before the cursor, where the read head is, was a B. Otherwise, the 7th state will never be reached, Q7. And if you're in Q7 and you see more characters, Q7 then goes nowhere and gets deactivated. So the only way to activate Q7 is if the 7th character before where you are now was actually a B. And if this is the end of the string, the whole thing stops and Q7 is still on, and that's accepting. Any other case, Q7 will be off. So if you think about it, any others, the only way to activate Q7, if and only if, is when the 7th character before the end was a B. So this machine does the job for that reason, and that's how it operates specifically on a particular string, and it's a non-deterministic machine. Now, you can convert this to a deterministic machine. In a minute, we'll talk about how to convert a non-deterministic machine to a deterministic machine in a general way that always works. And you get a machine that does the same job, except you lose the non-determinism. You get rid of it. You get a deterministic machine instead that does the exact same job. Any questions so far about non-determinism? So it's a generalization of determinism. You can be in multiple states simultaneously. And the number of states that can be active at any given moment could be any number between 1 and the whole machine. Actually, every single state could be active if it's some particular machine that gets you into that situation. All right, so here's why non-determinism can always be disposed of and eliminated, giving you a deterministic machine that does the same job. So it's not an essential superpower, non-determinism. For other machine models, it is an essential power. For push-down automata, for example, stack automata that accept context-free languages, we'll get to them in a couple of weeks. Non-determinism actually buys you extra recognition power. Non-deterministic push-down automata can do things that a deterministic push-down automata cannot do. But for finite automata, which is what we're on now, non-deterministic finite automata cannot do anything new besides what regular deterministic finite automata can do. So why do we use non-determinism? Well, it can simplify and reduce the size of the machine or the convenience of programming them, and many other benefits. We'll get to that separately. But here's how you can convert a non-deterministic machine into a deterministic machine, always, in a general way. So assume this is the computation tree for a particular non-deterministic machine, and this computation tree kind of bifurcates, and certain paths go to accepting states, other paths go to non-accepting states. Let's assume that the tree looks like this for a particular input, for a particular machine, but the construction will be general. So what we'll do is we're going to generalize the cross-product construction that we saw a few slides ago into a powerset construction. Instead of just having pairs of states, we'll have actual arbitrary subsets of states that can be active at any given time. So we'll have superstates that are made not of pairs, but of arbitrary subsets. Not just 2, but any number of states of the original machine. And the superstates will take you from one state to another via the super transition function in blue in a way that keeps the transitions consistent. So if this state gives rise to these two, and this state gives rise to this one, and this one gives rise to that one, and so on. So this whole collection of states here, this whole subset of states, will give rise to this whole subset of states in one single non-deterministic transition based on a single input character from the input string. Same as the power set of the cross-product construction, except this is more general because these states could be larger than 2, any number of states of the original machine. So the initial superstate, of course, will be the unique single state of the machine. That's the initial state. That doesn't change, same as the cross-product construction, right? And it's color-coded purple because it's the initial superstate. The final superstates are any superstate that has at least one final state in it. So it'd be this one and that one. So as long at least if there's at least one final substate that's a final state in each one of those superstates, that superstate will be a final superstate in the super machine that we're constructing. And again, the reason for that is as long as there's one path to success, we're good. So as long as one of them is final, the whole thing is final. And so the resulting deterministic finite automata that we're defining like this will simulate the non-deterministic finite automata because it will keep track of all the possible states that the non-deterministic machine can be in, except it will do so deterministically by virtue of which superstate it's in. So how many superstates can you have at most? If your original non-deterministic finite automata has k states in it, how many states at most will this super machine with all of its superstates, how many states could it have at most, this construction that we're constructing? Cardinality of the power set. And what is that for k elements? 2 to the k. So this machine can grow exponentially in size, but it will be deterministic. Okay. So it's like simulating all these multiple threads in parallel deterministically, and you don't rely on non-determinism anymore. And this machine will do the exact same job as the deterministic machine, except it will do it deterministically. You'll do the same job as the non-deterministic machine, except do it deterministically. And this is called a power set construction. Not to be confused with the cross-product construction, that's a special case of this. Okay, so this is like more powerful. Now, this construction won't work for push-down automata or for Turing machines. We'll talk about those later in the course. So it works for finite automata because the state of a finite automata doesn't depend on anything other than the state set and the symbol that you're looking at right now. It doesn't depend on the previous states or the contents of a tape or the contents of a stack, and so because there is no tape and there is no stack like we have in push-down automata or Turing machines respectively. But that's kind of jumping ahead. Let's focus on this for a little bit more. So the power set construction generalizes the cross-product construction, but it's more general because more combinations of states are possible than just pairs. So here's an example of the power set construction that we just did. Here's an example of the cross-product construction from a few slides ago, and you can see that it's more general and more state sets can be represented or resulted in. So for example, if here's an extra credit problem that uses the kind of this power set type construction, actually it's a little bit more general than that even. Half of a language is defined as the first halves of all even length strings in the language. So if you have a string that looks like VW in the language, only the V that gets taken into the half operator on that language. It's all the first halves of all even length strings in the language. Show that, for extra credit, show that this half operator preserves regularity. And similarly, a two-way finite automata is a finite automata where the read head can go backwards and forwards, either way. So just like before, it can only go in one direction, left to right, the read head, one character at a time. Now, the read head can go backwards on some transitions based on which state you're in and which character you're looking at. So sometimes you can go backwards and then forwards again, and then backwards again, and then more forwards. So you can go backwards and forwards. And you might think, well, that gets you more recognition power, but it doesn't. So for extra credit, prove that a two-way finite automata doesn't buy you anything extra. For every two-way finite automata that you can think of, there's a one-way finite automata that does the exact same job. That is, it recognizes the exact same languages as the first finite automata. That's two-way. Now, epsilon transitions are transitions for free. They're like free transitions. If you're in QI and you want to go to QJ based on no input processing at all, in other words, no input means you're processing an epsilon. It's equivalent logically, right? You're processing no characters or epsilon character. In other words, you immediately jump to another state without consuming any input characters. It turns out that You can always find a machine that doesn't have epsilon transitions that does the same thing, because basically epsilon transitions are a form of non-determinism. They're kind of a restricted, simple form of non-determinism where you can stay in Qi, or for free you can go to Qj, so in some sense you're in both. And you can proceed as if you were in either one. Basically you're non-deterministically now in both, if you invoke this non-deterministic epsilon transition. So using this kind of power set construction, you can also get rid of epsilon transitions. And basically, the epsilon transitions, therefore, do not buy you any extra recognition power. It's not a superpower. It's just simulatable deterministically using a power set type construction that gets rid of those two, along with any other kind of non-determinism that there is. So, but that doesn't mean you shouldn't have them at all, because sometimes it's convenient to have an epsilon transition when you express something or construct a machine, and getting rid of them might increase the size of the machine, just like getting rid of non-determinism can exponentiate the size of the machine, because the supersets, it could be 2 to the k of them for k states in the non-deterministic machine. So sometimes it's convenient and useful and instructive to have epsilon transitions, just like it's sometimes useful to construct a non-deterministic machine that does the job rather than a deterministic machine, because the non-deterministic one will be shorter, more succinct, and operate more simply. For example, in this example here that we did earlier, this machine has 7 states in it, actually 8. 8 states in this machine that recognizes characters in a way that the 7th character before the end of the string is a B. If you try to make this a deterministic machine using the power set construction, how many states do you think you'll have roughly? Take a wild guess. Roughly 2 to the 7th, right? Or at least 2 to the 6th. You'll have a lot of states, right? So, because you'll need to remember 6 characters sort of in your finite control, because if you have more characters beyond the current place where you're at, you cannot accept anymore, but you can remember all the previous characters. And so you got to kind of remember the last, 6 characters that you've seen to see if there's more characters, so that the 7th one will become the new one that now is only the 6th one. If you see one more character, it'll become the 7th one before the end. So you kind of have to remember roughly at least 6 characters, and 2 to the 6th is many dozens, right? So the size of this machine will blow up exponentially in this case roughly 2 to the 6th, and you'll get something like 60 or so states. Not all of them may be reachable, but a lot of them will be reachable. But this machine non-deterministically can do the job in only 7 states, and that's a win in terms of representation, coming up with the machine, programming it, debugging it, making sure it works, and so on, like if you do the JFlap, for example. So non-determinism has its uses. It reduces the size of the machine, makes it easier to construct, easier to explain why it works, and so on. And epsilon transitions, same thing. But the point is they're not essential. Non-determinism or epsilon transitions are not essential. You can always get rid of it by pulling the power set construction and forcing it to be completely deterministic, and therefore not employ non-determinism at all. Any questions or thoughts on this? Yeah.
Can you explain a little bit more about the definition of half?
Yeah, so half basically is defined as all V's such that VW is in L and V is equal in size to W. In other words, V is the first half of a string in L, which means that string is even. So V is the first half of some even length string.
Oh, so that's belongs to.
Yes, belong to. So if VW is in L and their sizes are equal, that means V is the first half and W is the second half of some string in L. You only take the first half. That's why we call it half. So we take only the first halves of all even length strings in L, and that's the new language that this operator defines.
What would that symbol be after the sigma star?
Right here?
Yeah.
Such that.
Such that.
It's like you could use a vertical bar alternatively, like the vertical bar, such that something is true. That's all. How many understand the definition of half? Okay. I'll take that. That's most of you. Any other questions about any of this? So again, epsilon transitions could be thought of as a super state with both of these states in it, and it could be either one or the other. Now, to actually do the conversion, you start writing down states that you're in, and as you write them, you write more and more states corresponding to more and more subsets, and eventually it has to peter out, and there'll be no more states to add, super states to add, because you would have reached, at the worst case, all possible subsets represented as super states. So this conversion will eventually terminate with potentially a very large deterministic machine, but it will terminate in every case. And in the second homework, I'm asking you to convert some non-deterministic machine to a deterministic machine and test it out in JFlap and so on. Make sure you understand this construction and how it works and so on. Now, there's a cool movie called Next by Nicolas Cage. It came out like maybe 10 years ago. And it's a guy that has a certain interesting superpower. The superpower of this person here is that it has a power of non-determinism. This character can bifurcate his reality several different directions and stick with the one that he likes best. So that's a very interesting technical superpower. Usually superpowers are kind of boring. Somebody's very strong, or they can fly through the air, or they can dive in the underwater, or whatever, or stop bullets, whatever. This one, is highly technical superpower. And in fact, the title of the movie, Next, refers to the transition function of the finite automata, the next state transition. Of course, most moviegoers won't know a lot about finite automata and formal languages to fully appreciate the movie, but it's still a fun movie. But if you know about non-determinism and transition function, the powerset construction, it makes an even more interesting movie. So for extra credit, you can watch this movie and tell me what you think. By the way, this guy in the movie, for a living, what he does, he's a gambler. So he gambles for a living. Think about it. You're sitting at the blackjack table and you say, stay or hit, or you're sitting at the roulette table and you say black or white, bet, or so he can sort of see different realities based on what the decision will be, and sees where he will lose, where he will win, and stick with the one that he wins. And he makes a lot of money gambling. Of course, he has to be very careful too, because if he wins too much all the time, the casino will be suspicious, and then he will have even bigger problems than money. So also it helps him kind of romantically pursue some woman that he likes, because he comes up to her in a bar and gives her some line, and she kind of disses him because she thinks it's kind of tacky. So then some other path, he uses some other line. Finally, he finds a path where he finds a line that she actually likes, and he goes with that, and he makes a nice romance and everything. So very, very useful superpower. So it's kind of an interesting, cute movie. So any questions so far about non-determinism? Except why do we care about non-determinism? So here's the top 10 reasons why we study non-determinism. So first of all, it's a study of parallelism or concurrency. And everything in the universe is concurrent, right? Even in your brain, there's a lot of different threads going on concurrently, right? The part of your brain that operates your heart and lungs and bloodstream and so on, completely independent for the part that causes you to speak or to see or to feel or to hear. And it's a good thing that there's separate parts of the brain, because if it was happening in serial, while you were talking, your heart wouldn't be pumping or your lungs wouldn't be breathing, then you'll be in trouble. Right? So you have a lot of concurrency going on in your brain. The computer, same thing. Your computer has dozens and even hundreds of threads running simultaneously in your operating system, whether it's Windows 10 or your smartphones, a lot of things happening at the same time, right? So non-determinism is a model of concurrency or parallelism. So by studying it, we study parallelism in general. And that's a very, very useful property to have, parallelism and concurrency. It also illuminates the structure of problems. Some problems are inherently concurrent or parallel, and it tells you a lot about this stuff. It saves you time and effort by solving intractable problems much more efficiently, like NP-complete problems. We'll talk about NP-completeness separately, but if you want to solve NP-complete problems, parallelism and non-determinism is a big help in that, because you have to explore multiple paths in a solution space concurrently or simultaneously. And so it helps you study the notion of intractability, what's intractable and what's not intractable, and how these intractable problems relate to one another and so on. Basically, it also sheds light on deep connections and completeness theories that cover entire sets of problems rather than individual problems individually. So using non-determinism and non-deterministic kind of principles, it allows you to solve big classes of problems at the same time rather than attack them individually, which again is a great force multiplier or advantage, if you will, in solving problems. It helps you understand and explain why verifying proofs and solutions is easier than coming up with them to begin with. So you already seen in this class and other classes that if somebody tells you what the answer is, understanding their answer is easier than coming up with the answer to begin with on your own. And this kind of non-deterministic kind of results and non-determinism in general helps you understand this trend. And in some scenarios, it's not even easier. It's the same difficulty of understanding a proof and coming up with it to begin. It's modulus and polynomial time. So there's a lot of interesting issues there that non-determinism addresses and sheds light on. It gives rise to entire new mathematical ways of proving things and analyzing things and approaching problems. And so whole new types of mathematics were induced by studying non-determinism, and that's valuable in itself. For example, zero-knowledge proofs. And a lot of crypto was based on studies of non-determinism and the implications thereof. Also, it decouples the abstract complexity of a problem from the actual platform that tries to solve the problem or run the code that solves the problem. So, for example, the classes P and NP, polynomial time and non-deterministic polynomial time, for a PC, and that same class for an iPhone, and the same class for a supercomputer, and the same class for an abacus, for that matter, which is a very slow computer made of beads. Those classes are the same for all of these computation models. So if you have results and problems and solutions and insights and theorems about these classes, those theorems and results apply to all of these computation models, not just to a particular computer like a Dell precision workstation, but also to every other model that we know of, including other models altogether besides silicon-based computers, such as biological computers, like we are, right? We are biological computers. Look in the mirror, you'll see one, right? So the classes P and NP apply to us too, and they apply also to cellular automata-based computers or lambda calculus type computation models, or computing using Lego bricks, and smart Lego systems, or Tinker Toys, or nuts and bolts computers, mechanical computers like Babbage's analytical engine and any other mechanical computer, or any other type of computation system that we know of. They all have the same kind of mathematical complexity classes like P and NP and P space, and we'll talk more specifically about those later in the semester. So anyway, the study of non-determinism decouples these classes from the actual underlying machines that implement and compute and utilize, these computations in practice, and that's a very, very good property to have, which means any results that you have, any algorithms you come up with, apply to all of these platforms, and even to platforms that we don't know about yet. Some computer that we'll have in 100 years from now, and we have no idea what it will look like, will probably have the same P and NP and P space complexity classes as the computers do today. We're very sure of that, actually, and for good scientific reasons. It's not just a hope, but rather a mathematical truism. So that's another advantage of non-determinism, and it helps you identify disciplined ways to detect the hardest problems in the class. So for example, for the class NP, the hardest problem is satisfiability, Boolean satisfiability, or traveling salesman, or colorability, or packing and binning kind of problems. Those are all equivalent modulo polynomial time, and the study of non-determinism helps you identify what's hardest for a particular class. If you attack that problem reasonably well, you've basically solved the entire class reasonably well as well. So that enables you to solve problems in bundles. You solve an entire class of problems simultaneously with the same algorithm, rather than attack them individually, and there's an infinite number of problems in the class. So that's a huge advantage, a force multiplier, if you will, big piece of leverage that you can have over large collections of problems that you can solve all at the same time in one fell swoop, rather than just do it individually. And it helps forge unifications between many fields, including logic and computer science and math and additional fields as well. So never forget an important reason that it's fun and cool and interesting to study something. Never underestimate that reason. So it's a lot of benefits for studying non-determinism. All right. Let's any questions or issues about non-determinism? We'll get back to that subject again and again. This is just the tip of an iceberg here. All right, so let's talk about regular expressions. Regular expressions are a way to represent regular languages. Just like finite automata gives rise to regular languages, we'll see that regular expressions are equivalent to finite automata in terms of the languages that they represent or denote. Okay? So regular expressions are defined inductively. The base cases are simple. The empty set is a regular expression, or more specifically, more precisely, the empty set is a language denoted by this regular expression here, denoting the empty set. The trivial language is a language that contains only the empty string, and that's a regular expression too. It looks like this, denoting that trivial language. And there's the singleton languages that only have a single string in it, and that string is equal to a single character from the alphabet, like an A or a B or a 0 or a 1, but not any longer strings in size, 1 character long. So those are the single language. So all these 3 cases in green are the base cases of regular expressions. And the other few rules, 3 rules, tell you how to compose these repeatedly using certain operators. For example, union, concatenation, and clean closure are the 3 main regular expression operators. So the union of 2 regular expressions is another regular expression. The union is denoted as a plus here. And we use parentheses to disambiguate order of operations and so on. The concatenation is just denoted as a product. So if R and S are regular expressions, so is R times S, denoting the concatenation of the 2 languages represented by these 2 regular expressions respectively. And of course the clean closure. So if R is a regular expression, so is R star, also a regular expression. And R star denotes the clean closure of the language denoted by the regular expression R. Notice I'm using types here very deliberately in my speech. I'm being very precise and very deliberate, very intentional and accurate in my speech, as much as I can muster. Right? So I don't say that R star is a language. It's not. R star is a regular expression. It denotes a language. Okay, so notice the difference in semantics between these types and objects that I'm referring to. And I urge you to try to be very precise yourself, both in your speech and in your thinking and analysis. So here are examples of some regular expressions composed out of these operators, right? The base cases, like the A and the B and so on, and then the applications of union, the plus, and concatenation, which is the times, and of course the clean closure, which is the star. So here's the first theorem about regular expressions. Any regular expression denotes a language accepted by some finite automata. Now, when I wrote this down here, I made a type error on purpose. Right? So I said any regular expression is accepted by some finite automata. A finite automata doesn't accept a regular expression. It accepts a language. Right? A regular expression denotes a language that then the finite automata can accept. But I put this type error here on purpose just so you can see it staring at you. And hopefully you can see the type error right there. It's like that commercial, The Most Interesting Man in the World. Once he had an awkward moment just to see what it's like. Right? So I made a deliberate type error. I'll try not to do that inadvertently. Okay, so why is that theorem true? That whenever you have a regular expression, it denotes a language is accepted by some finite automata. Well, we're going to track these constructions. So for accepting the empty set, here's a finite automata that accepts the empty string. The empty set is nothing, no strings whatsoever. It's a set, but it's a set containing nothing. So here's a finite automata. This is a complete finite automata. There's an initial state in purple here, no transitions, no other states, no final states. So once it executes, it will never accept anything. In other words, this finite automata right here will accept the empty set. How many can see that? Okay, simple. The trivial language is accepted by a slightly modified finite automata. This initial state and final state are the same state. So this machine here has a final state. It has an initial state. They're the same state, happen to be. The final and the initial state are one and the same. And there's no other transition, so it accepts the trivial language containing the empty string. So this accepts the empty string. This one doesn't. In fact, this one doesn't accept anything. So this machine here accepts the trivial language containing the empty string and nothing else. And then to accept a singleton language, all you got to do is start somewhere, and on that singleton character, this one string that's made of 1 character long, go to a final state, and then don't go anywhere else, hang on any other transitions. And so you can always trivially accept a singleton language when a machine looks like this. How many understand all 3 cases here? Okay, any questions? Yeah.
So empty set doesn't represent any language.
So the empty set represents one particular language that has no strings in it, and it's the unique language that contains 0 strings. It's not any language. It's a language. It's a very specific language, the one that has no strings in it whatsoever. And there's only one of those.
And
It's unique.
and the finite automata doesn't contain any final state?
No, there's no final state, which means it can't accept anything, which means it accepts exactly the empty set. No more, no less.
Okay, so it doesn't accept anything, but it accepts the language that doesn't contain any string.
Okay, so that's a nice hair to split. So let me paraphrase it. So it accepts a language containing no strings. So it accepts no strings whatsoever. But it's correct to say it accepts a language. So it doesn't accept nothing. It accepts no strings. But the language it accepts, it's the empty language, containing no strings in it.
And it doesn't have any final state.
And it has no final state, so it can't accept any strings. But the language it accepts as a set is the empty language. It still accepts a language, the empty language. The language happens to have no strings in it because it doesn't accept any strings. Because it can't accept any strings for one good reason. It has no final states. In fact, it has no transitions even, never mind a final state. It has no other non-final states other than the initial state. So technically, you're correct. It accepts a language, the empty language. But it accepts no strings. And the empty language, sure enough, has no strings, so we're good. But that's a nice differentiation of the semantics that so I'm glad you're thinking that way, because you're being very precise, and that's good. Precision is good. Yeah, question is? Okay. All right. So in order to accept the union of the two languages denoted by two regular expressions, you can jump from a new start state to the start states of these two machines that accept the languages represented by these two regular expressions respectively. And this is what you were talking about earlier. To accept the union, you just basically jump non-deterministically with epsilon transitions to either one machine or the other or both. And then within these machines, you accept either the first language or the second language of the two machines respectively. And therefore, you accept the union. So this finite automata construction here from the two machines that accept the languages represented by these two regular expressions R and S, this construction accepts the union of R and S, the language represented by the union of R and S, by the regular expression R plus S. How many understand this construction here? So it's pretty straightforward. Concatenation is almost as straightforward as that, except instead of doing it in parallel, you do it in serial. So you start by executing the first machine from its start state. You execute in the first. For every final state in the first machine, you jump for free using epsilon to the start state of the second machine. And it could be many jumps, because it could be many final states. I just showed you one here in green, but it could be many others. And you jump from all of them to the initial state of the second machine. Once you do that, you execute in the second machine. And together, you accepted a string in the language denoted by the concatenation of these two regular expressions, R and S, respectively. How many understand the second construction? Okay, any questions so far? It's relatively straightforward. So we're surgically manipulating and splicing and mashing these two machines together to either get the union or the concatenation. Do it either in parallel or in serial. Now, to get the clean closure, it's a similar process. You start with this machine that accepts the language denoted by the regular expression R, and to get R star, you have to loop back from the final states of this machine back to its initial state and loop through this machine over and over and over again, concatenating everything together, and now you've accepted something in the language denoted by R star. And notice that we also have the option of going from the initial state to some other state that's a final state. That's where the epsilon comes in. Because remember, the R star is epsilon plus L squared plus L cubed, plus means union. So that gives you the base case here. But you keep cycling, iterating over that machine over and over again. Now, every time you iterate through the machine, you may accept a different string than the previous iteration. How many get that? A different string. It doesn't have to be the same, or it could be the same string, but it doesn't have to be the same string. Every iteration here could accept a different string than before. And that matches with the definition of clean closure, because when you square a language, the string in the first L could be different than the string in the second L when you concatenate the two. How many get that? It doesn't have to be the same. Good. So it's an important point. All right. Which means now we have a mechanical means of coming up with a finite automata to accept the language represented by any regular expression based on repetition of these and merging of these individual constructions. All right? Apply them inductively, recursively, repeatedly, and you can convert any arbitrary regular expression into a finite automata. Now, doing the opposite is much harder, and we'll get to that. So it's basically composition rules, right? You can compose these rules over and over again and come up with arbitrary machines to recognize arbitrary regular expressions, or the languages denoted by arbitrary regular expressions. So in the book, we're on page 59 to 62. We just proved that the class of regular languages close under star, clean closure, and union, and so on. And just showing you where we are in the book, so when you read the book, you know where to look. All right, so you can build by compositions these machines. So let's do an example of that. So let's say we want to construct a finite automata for a language where sum b precedes sum a. Right? All strings in sigma star where sum b precedes sum a. How do you do that? Well, you can represent it as a b and an a with sigma star before, in the middle, and after the b and the a, respectively. Or you can say, well, that's also true when you have a b right before an a. If you have a b finally that becomes an a as you go down the string, there'll be a place where the b goes into an a directly in the next character. How many believe that? Okay, so write it like that. It's a little bit shorter, it's a little bit simpler. So we'll do it that way. So here's the b and the a, the machine that accepts one b, the machine accepts one a, and we compose them like this by jumping from the final state of this machine to the initial state of that machine, and together we have a machine that accepts a b and then an a. And we compose these two rules from the previous slide. Which rules? We compose this rule twice in this manner here of concatenation. Right? So we got that. So that's the machine for the BA. Now the machine for the A plus B star, here's a machine for the A, same as here. Here's a machine for the B. Now we got to combine them as the union. So we jump from a new start state, epsilon transitions into the A and the B machine. And that's the machine that accepts either an A or the B, right? Now to get the star, you jump from the final states back to the initial state, and you keep cycling around like that. And the same thing happens here. I won't bother to analyze it again. It's just a copy of what's happening here, because you have A star, you have sigma star here and sigma star here, right? And then you got to concatenate this first third to the middle third to the last third. So again, that's a surgical splicing using the concatenation composition rule. So you get from the final states of this machine back to the initial state of this new machine, and from the final states of this machine to the initial state of that machine. And now these states are no longer final because you jump to here, and this state is no longer final, but these states are still final in the last machine. But you get this machine down here. I just copied it. If you want to see it in instant replay, there you go. I just love PowerPoint. I don't know about you, but so here's this machine here, and now we're going to eliminate these as final states. They're no longer final. These are the final states. How many understand that that's what we got to do? Because we compose them together, and we got to go through the whole construction. And so these used to be final states are no longer final states. But the rest of the machine stays the same. And now we're going to try to minimize it because it's too big. Right? So the idea behind minimizing a finite automata is you try to find equivalent states and merge them together. Right? So here's the machine again from the previous slide, unmodified. But now you notice that this epsilon transition here doesn't buy you anything. If you get to here, then you immediately go there, and you might as well merge these two states into a single state. How many see you can do that? It doesn't change anything, right? And you can similarly merge these two states, right? And so let's do that. So these two states become this state here, and these two states become this state here. And this machine still does the same job as before. It's just smaller. It's two states shorter than the previous machine. So once you do that, you find other states that can be merged. These two could be merged. These two could be merged. This could be merged here, and so on. And then you get an even smaller machine with these mergings going on. And then you keep finding states that you can merge, right? So these two states can now be merged right? And then these three states can be merged, and then you get even smaller machine with less states, right? And the mergings, happen to collapse these three states and these three states. And now these two states can be merged because epsilon, going to here, you might as well merge these two states together and those two states together. Now you get a much smaller machine down here. And look at this. This machine gives you any A's and B's, followed by a BA, then followed by any A's and B's again, and that kind of matches this regular expression here. Any A's and B's, followed by a BA, followed by any A's and B's. Now, we could have written this much more straightforward right away. We could have written this like that down here. But this process was mechanical. It was systematic. It works for any possible regular expression without having to think about it. Right? You can always do that and then minimize. Or you don't even have to minimize that. This here is a perfectly valid finite automata that does the job. This is just a simpler, shorter one that also does the job. So shorter, simpler is usually better, so you might as well minimize it while you're at it if you can. So we went from 16 states up here to only 3 states down here. That's like shortening up your program by getting rid of unnecessary code. Now, shortening it to an absolute minimum degree is not necessarily always great with code, because that also obfuscates the code, potentially. You can make it less readable and more bizarre looking, and yeah, it'll be less characters or less lines, but not necessarily better code. More maintainable, more understandable, more straightforward code, right? So you have to take that into account when you code. It's not, minimum number is not necessarily always the best in terms of lines of code or states in the machine. But the point is you can do this. And there's an algorithm from early 70s that can do this in n log n time. Do what in n log n? Minimize a given deterministic finite automata to the smallest possible number of states by identifying equivalent states and merging them together repeatedly like we did in the previous example. So it's a well-known, half-a-century-old algorithm now, and it's based on work that was done even earlier in the 50s. Now, I should say that minimizing the states in a non-deterministic machine, that we don't know how to do efficiently, although that's doable also, but we don't know how to do that efficiently meaning in polynomial time. So there's no known algorithm to minimize a non-deterministic finite automata. What we this algorithm works on deterministic machines only. Okay. A non-deterministic machine, there is an algorithm, it just runs in exponential time. Right? I mean, you can do it, it's just we don't know how to do it efficiently. What you can do is take the non-deterministic machine, run it through the powerset construction, then come up with a deterministic machine, and then minimize that using this algorithm. How many get that? You can do that. But that's not necessarily the smallest non-deterministic machine. It'll be the smallest deterministic machine. It's equivalent to the original arbitrary non-deterministic one. But it'll be a deterministic machine, not a non-deterministic machine, once you minimize it. So just wanted to bring that to your attention. Now, in case you're thinking about minimizing push-down automata or minimizing Turing machines, all bets are off. It's not so simple. Not only that, it's actually undecidable. It's uncomputable. There's no possible algorithm to minimize a push-down automata or a Turing machine. Okay. So I'm telling you, it's undecidable. For finite automata, it's relatively easy, n log n time. For non-deterministic finite automata, it's harder. It's exponential time, but still doable. For Turing machines, it's undecidable, uncomputable. For code, what do you think it is for code, for program? You see? How many say it's undecidable for code also? Intuitive. I'm not asking for a proof. Yeah, you're right. Undecidable. Why? Because arbitrary code can simulate arbitrary Turing machines. And if you can do it for code, you'll be able to do it for Turing machines. But I just told you can't do it for Turing machines. Undecidable. So minimizing a program to the least number of lines or the least number of characters of code, whether you're working in C++ or Java or Perl or any other programming language, undecidable, turns out. Question? Yeah, it's in NP, and we don't know if it's in P. We don't know if it's in a deterministic polynomial. We know it's a non-deterministic polynomial time. So there's a non-deterministic way of doing it, and the non-deterministic algorithm is relatively straightforward. Basically, guess what this what the smaller one is.
Is it verifiable that if I give you, if I say this is a minimal NFA, can we easily
So the way you would state it is you would ask, is there an automata that is smaller than k states, and you give me k also. So it's just like traveling salesman. For traveling salesman, so is there a tour of less than size k units of length? And so the answer will either be yes or no. So non-deterministically, you can find one of less than that many. So you may have to give the number of states as a parameter, but it is one of those problems that's in NP, but we don't know if it's also in P. It's just it's still an open problem. Now, whether it's NP-complete, I don't think it's NP-complete. It's not as general as arbitrary, Boolean satisfiability or knapsack problem or one of those NP-complete problems. But it is, there's non-deterministic algorithms for it. We don't know how to do it deterministically in polynomial time. But it's an important problem. I mean, it'd be nice if we knew how to do that. But we don't. Also, you cannot minimize a regular expression in polynomial time that we know of. We know of no algorithm to minimize regular expressions either. So if I give you a regular expression like I did, a few slides ago, I said, remember that there's, a regular expression here, but this is a smaller regular expression. We don't know how to do that either. In a couple of slides, we'll see another example of kind of minimizing a regular expression into a smaller one. Right. So, any other questions about any of this? So we've seen how to minimize deterministic finite automata. We've seen it can be done quickly. We said that it can be done for arbitrary Turing machines or even pieces of code or Push-down automata for that matter. So when it comes to context-free grammars, the notion of minimizing a grammar to the least number of productions of variables also is undecidable, actually. So it's worse than NP. It's just undecidable. So minimizing things is actually a very tough problem in general. Coming up with minimal model of computation that does the same as this other computation model, whether it's a piece of code, a Turing machine, a push-down automata, those usually tend to be undecidable problems. Question?
How long does it take to convert the non-deterministic to deterministic?
You tell me. If you want to convert a non-deterministic machine to a deterministic machine using the powerset construction, in the worst case, how long will it take? Exponential time. Simply because the output will be exponential, right? The deterministic version could be exponential number of states. And just to list them out will be exponential time, much less to derive them. So if you're trying to get at the fine point to minimize a non-deterministic finite automata, first convert it to a deterministic finite automata and then minimize that won't be efficient either. Because the blow-up could be exponential right off the bat. And even then, you'll end up with a deterministic finite automata, and you still haven't solved the problem of converting that deterministic one to a non-deterministic version that's even smaller. That step isn't even included in all that trouble that you went through. So it's tricky business. It's not at all straightforward. Now, so basically, so far we've shown that every regular expression has a finite automata that recognizes the same language denoted by that regular expression. That's one direction. Now we're about to prove the opposite direction. The opposite direction is trickier. The opposite direction is whenever you have, conversely, a finite automata, there is some regular expression that denotes the same language accepted by that finite automata. So together, these two results, these two theorems, will be an if and only if. It will be a complete characterization of the regular languages as regular expression equivalents. Okay? For every one, there's one of the other that does the same job, and vice versa. So now we're showing the other direction. How many see this plan of what we're doing? Okay, that's where we're going next. So how do we do that? We're going to come up with a notion of generalized finite automata where every transition between two states has not just a character on it, triggered by it has a regular expression on it, that any series of characters in the input matching that regular expression can trigger that transition now. Okay, so here's what's going to happen. We're going to have one super start state and one super final state, and we're going to augment all the other missing transitions with new transitions that initially will be the empty set, But at the end, we'll have actual regular expressions on them until the whole machine minimizes to a single pair of states, the super start state and a super final state. So here's the original finite automata M. Here's its initial state, and here are its final states. What we're going to do is generalize it. So we're going to have a super new super transition, a super initial state, and a new super final state. Go from this initial state to the initial state there on an epsilon, and go from the final states here to this new final state on epsilons. And now have all these other transitions put in from the initial state to all the other states, and from all the other states to the final state, but put the empty regular expression on it, which means they can't be triggered yet. Because these are new transitions that weren't there before, and I don't want to trigger them arbitrarily. So right now, because they have the empty symbol, that means they're never going to be triggered as they stand right now. So this machine is equivalent to that machine. How many get that? Now you'll see in a minute why I wrote it this way. Because I want all possible edges to be there. I want this to be essentially a complete graph, in some sense, right? Or at least, have all these extra blue transitions going on there. So it is a complete graph, because every state has transition to all other states, including itself. I'm going to have all these self loops in here with empty regular expression written on each and every one of those new blue states that weren't there before. So it's a complete graph. You'll see in a minute why I want a complete graph. But this machine right now is not any different than that machine in terms of the language it accepts. Because all these new transitions I put in blue never get triggered so far because they all have the empty set on them, so nothing triggers them. So it's as if they're not there, which means this machine is equivalent to that machine. How many see that part? Good. Any questions so far? We're not done. This is just the initial step. Now this is a generalized finite automata, because now arcs can be labeled not just with individual characters or symbols, but with actual long and complicated regular expressions as well. And here are the self arcs. Right? And you can go from a state to itself using epsilon, and that doesn't change anything either. Because if you're already there, you might as well go to yourself and you're still there, and you haven't done anything. You haven't consumed any input because it's an epsilon transition. But here's what this allows you to do. It allows you to reduce this generalized finite automata by one state at a time until it's as small as possible, and it's still equivalent. So here's the transformation step. So let's say you have a triple of states, qi, qj, and some q prime that look like this. It's a triangle here. Right? qi goes to q prime goes to qj, and these three regular expressions on these four arcs are p, r, t, and s. And you can always find such a triangle in this generalized finite automata. Why is that? Why can you always find such a triangle of states that has this kind of structure? Because all the transitions are there. It's a complete graph. Right? It's a complete graph, including all these self-transitions. Right? Every state also goes to itself on an epsilon, and every state goes to every other state with initially just empty regular expressions on these arcs. But it's a complete graph. So in a complete graph, you can always find a triangle. How many understand that? And that's why I made a complete graph, so I can always find a triangle like that. But now when I find a triangle, here's what I'm going to do. Given this triangle, it looks like this. I'm going to replace it with only a pair. I'm going to eliminate one of these three states. So what I'm going to do is keep I and j as states, qi and qj, keep the p there, but then replace this state here by another transition, goes from qi and qj bypassing this state. But what does this state bias? You can go with a p from here to here, or you can go from here to here, not using a p, but going the long way, take an r, and then take s however many times you want, and then take a t, and you'll still make this transition from I to j via q naught. So getting rid of q naught basically replaces this state with r s star t on this other arc between qi and qj, and we eliminated this intermediate step qi, and instead allow this kind of transition. How many understand this or see this? Okay, and this is still equivalent. I can go from here to here using the direct method, using whatever regular expression p is, or r s star t, and eliminate q naught. But now I can merge these two states. or these two transitions between these two states. There's a P here and an RS star T here, so I can merge them together into what? P or union RS star T. And now I've eliminated this other edge as well. So now I have the equivalent machine. This is only for this triple. The rest of the machine remains intact. I just showed you the surgical manipulation, the surgical manipulation of this triple from here to here, and the rest of the machine stays intact. So I haven't changed the functionality of the machine. I just reduced it by one state. And this regular expression on this arc became more complicated. But that's okay. The machine has one less state in it. Now what am I going to do? One word? Repeat. Thank you. And repeat. And it's always a triangle because it's still a complete graph. And I can do this again and again and again. And at the end, I'll have only two states left. The initial superstate and the final superstate. And whatever regular expression ends up labeling this single transition between these two states will represent what? Not a trick question. The regular expression of the language of the entire original machine that I started with. And that's how I can convert an arbitrary finite automata into regular expression equivalent. And this always works. So the label of the last remaining transition, only one left, after I eliminated repeatedly each and every state and eventually every single arc, will be the language, will correspond to the language of the original machine. And that's a general proof and a general transition kind of manipulation. Yeah, somebody solved that problem. Go.
Extra credit.
Extra credit? You want extra credit? Maybe pass the key through the. Oh, okay, good. I guess it's a wait a second. All right. So this technique always works. Can handle an arbitrary finite automata and end up with the regular expression corresponding to the language accepted by that finite automata. So now we prove the other half of the theorem. So remember what the first half was, right? For every regular expression, we came up with a finite automata that accepts the same language that that regular expression represents. Here, they did the opposite. For every finite automata, we came up with a regular expression that represents the language accepted by that finite automata. So now we're saying that we have a complete characterization of the regular languages, either by finite automata on one hand, or by regular expressions on the other hand. In other words, the finite automata and the regular expressions denote the same class of languages, namely the regular languages. So now we have two characterizations, two separate different characterizations of the regular languages. One by machines, by finite automata, and the other characterization is by regular expressions, and they're two separate animals. The regular expression is not a machine. Right? It doesn't have any transitions, and it doesn't have any states, it's just an expression. A machine is not a regular expression. It has states and transitions and final state and end state and blah, blah, blah. And yet, these two types of objects represent the exact same class of languages, which is nice to know. And so now you know why regular expressions are so powerful, so ubiquitous, so useful, because they represent exactly the regular languages. Alternatively, they represent exactly what finite automatas can do. Precisely. Completely. It's a complete, precise, clean characterization. Right? There's no exceptions. So a regular expression is as good as a finite automata and vice versa. Finite automata is as good as a regular expression in terms of what it can represent or denote. Okay, any questions about any of this? Yeah.
You mentioned that this can be used to use some regular expression, but how to define the sum? Like, after you get the regular expression from the finite automata, then you can expand or reduce that regular expression.
Yeah, so when you do this, the regular expression ending up on this arc will not necessarily be the smallest one possible. It could be too long compared to the minimum one that will do the job. But it'll be correct. That regular expression ending up on this arc will represent the language accepted by the original finite automata that you started with.
But what's the best and worst case?
The worst case, it could be considerably larger, but it won't be exponentially large, right? So, for example, this transition gets rid of a state and only adds what was on the other arcs, right? In other words, there was no new additions other than this union plus a star operator. So you have an extra union, an extra star, but the original P, R, S, and T are still here. P, R, S, and T. So if you start with this machine and you add all these arcs, and at the end the regular expression will have sort of the union of whatever is in all the arcs. Some of it will be starred, otherwise will be unioned in, but you won't have more than the sum of total of all the symbols on all the arcs. And a lot of them will be the empty set. So you get rid of it. That will kind of vanish, right? So it will not be larger than the size of the original machine in terms of all the extra arcs that were added in. And because it was a complete graph, it could be the square of the number of states. So that's a very good question she's asking. She's asking how big, how inefficient will this extra final regular expression be as a function of how small it could actually be if you minimized it? And the answer is quadratic, at worst. And sometimes it won't even be that bad. And even if it's quadratic, you could still probably minimize it quite a bit before you run out of clever ways to minimize it. And if you're willing to minimize it using exponential time, you can minimize it to the smallest possible. And we just don't know how to minimize it using polynomial time, deterministically. Okay. So again, so what we have is a complete characterization of the class of regular languages either by finite automatas or regular expressions equivalently. So now we'll almost use them interchangeably. If you want to show a language is regular, now we have two different ways of showing it's regular. Put a finite automata that accepts it, or a regular expression that represents it. Your choice. Either one will establish that it's regular, because now we know these two representations or characterizations are equivalent to one another. That's a good thing. And there's other equivalent representations too, besides those two. But we'll just stay with those for a while. And in terms of the book, this happens on page 70, 71, 72. There's the generalized deterministic finite automata, or non-deterministic rather, finite automata. Here's this triangle, right? And I call it R, S, T, but here it's called R1, R2, R2. And here's the concatenation of something with the star of this R2, with this concatenation of the R3, and it's the union with the R4, and this whole triangle became this pair. How many see that this is what I had in the previous slide using colors? Okay, it's the same thing that it is in page 72 of the book, just so when you read the book, and I urge you to read the book, don't make the mistake of thinking get away without reading the book, because the book explains certain things differently than I do, and it explains some things that I don't, and I explain some things that are not in the book, so it's not exactly equivalent to what's going on in this class here. I'll give you a lot of insights that aren't in the book. But the book will give you some results that I will not necessarily mention in class because there's not enough time to go over everything. So you need to read the book, basically. So I'll keep showing you the equivalences, the correspondences, the exact pages in the book where these things appear so you know exactly. So you can't say you didn't know. Okay, here are some regular expressions, identities. So the union is commutative, right? Concatenation is associative, right? What two rules are these? Distributive rules of concatenation over union. These are always true for any regular expressions or languages for that matter, R and S and T. The star of the empty set is simply the empty string, right? Or more precisely, the set containing the empty string. The empty set is the identity element with respect to union. The empty string is the identity element with respect to concatenation. But notice that you can't interchange them. You can't say that the empty string is the identity element with respect to union. It isn't. It's the identity element with respect to concatenation, not the other way around. If you say epsilon plus R and you star that, it's the same as starring it to begin with. And the least obvious identity here on this list is R star S star quantity star is the same as R plus S quantity star. Now it's not hard to show that, but it's a theorem. It's not. None of these are axioms. They're theorems. They follow from the definition of these operators, and this is kind of interesting to prove. You know, it's just a few lines of argument. But again, to show that two sets are the same, show that A is a subset of B and B is a subset of A separately, and together these two results will show that they're one and the same set. That's a typical strategy to show that sets are equivalent. Any thoughts, comments, questions about any of this? Regular expressions, finite automata, why they're equivalent, how to convert one to the other. So, yeah, question.
So R is, looking at the R gets concatenated by empty language, the red one, the second red one. No, the second one.
Yes.
Yeah. Is it because this concatenation is not defined, or?
So how is concatenation defined? That's a good point of definition. Concatenation is every element from one concatenated with every element from the other. So if one of the two sets is empty, what is the concatenation according to this definition? It's every element from R concatenated with every element from the empty set. But the empty set has no elements. So what will that equal to once you end up with the empty set? Because there's nothing to concatenate with, so the answer will be empty, simply from the definition.
Is that because they're different types, so that there's no such operation?
Well, they're not different types. Remember the definition of regular expression. So whenever you wonder about that, let's go back to the definition of regular expressions. The empty set is a regular expression. It's one of the base cases. So there's no type error there. But it's a very good question to ask. Is there a type error? Are they the same type? Because you cannot concatenate things of different types. You cannot concatenate a string to a dog. I mean, it doesn't make sense, right? It's kind of funny if you even try, mention trying to do that, right? So it's important to worry about the types, right? So technically, there's no type error there. It's just there's no elements there to concatenate. The answer will be the empty set. Any other thoughts or questions? No. Okay, so here are some decidable finite automata problems. So something is decidable if there's an algorithm for it, right? I know it sounds obvious, like when will it not have an algorithm? Well, we already saw that the halting problem is something that's very well defined for which there's no algorithm. And many other problems, in fact, there's an uncountable number of functions that have no algorithms for it. So it's not trivial, and certainly we can't take it for granted that there's an algorithm for everything in the universe, and many things don't have algorithms. So I'll give you two finite automata, M1 and M2, and I say, is the language of the first one empty? I give you a finite automata, say, is its language empty? What's an algorithm to determine that? How can you tell me if its language is empty or not empty? This one is not hard. If there's a final state, certainly if there's no final state, the language can't have anything in it because it can't accept anything because there's no final state to accept with. But is that enough? If there is a final state, must it accept some strings? Yeah, so not only should there be a final state, but there should be a way to reach the final state from the initial state. Because if there's a final state, it doesn't do you any good if it's not reachable. If there's no arrows and arcs going into it through some path. So basically, it's a graph reachability problem. Here's the finite automata, and you're asking basically, is there a path from an initial state to some final state? Which final state? Any one you want, it doesn't matter. And if there is a path going from here, yeah, the language is not empty. And if there is no path, it is empty. So that's very easy to determine that. It's just path in a graph reachability. How fast can you do it as a function of the size of the graph? Algorithmically, how fast will it run? If you're not wasteful in terms of computation. Take a wild guess. Quadratic?
Yeah.
Certainly you can do it in quadratic time. How many say you can do it within quadratic time? Sure. Can you do it any faster? How many say you can do it in linear time? Okay. which doesn't contradict the fact that you can do it in quadratic time, right? If you can do a job in 3 hours, right, it doesn't exclude the notion that you can possibly do it in 1 hour if you're more careful, right? Certainly if you can do it in 1 hour, you can certainly take 3 hours by being very leisurely about it, right? Okay, so not only it's doable very quickly in linear time. All right, if I ask you, is the language of a finite automata infinite? Does it accept an infinite number of strings or only a finite number of strings in its language? How can you determine that?
Check if there's a clean stuff.
Okay. What do the rest of you say? Yeah.
For a cycle.
Check for a cycle. So if there's a cycle in there, but is a cycle enough? Let's say this finite automata has some cycle in it somewhere.
It needs to be a spot.
The cycle has to be reachable. Yeah, the cycle has to be reachable from the initial state, and from the cycle you must be able to reach some final state, then the language is infinite. So there's 3 conditions. 1, there must be a cycle. 2, the cycle must be reachable from the initial state. 3, from that cycle you must be able to reach a final state. So you're looking for some sort of a cycle. It's a cycle detection kind of situation, right? And there's the cycle around this state here. There's a cycle in blue, and that cycle must be reachable from the initial state. That some final state must be reachable from the cycle. Which final state? I don't care. Some final state. But there's an extra condition here that we haven't mentioned yet. There's a 4th condition. What do you think that might be? This one is more subtle. We're asking whether the language is infinite or not. If it's infinite, there's bigger and bigger and bigger strings. How many get that? Because if the string length was bounded by 1,000, then there's only a finite number of strings of size less than 1,000. So infinite language means arbitrarily large strings, which means a cycle. But there's a condition that nobody mentioned yet. This one is subtle. Some string on a cycle. That cycle must contain a string. Of what kind of string? Non-epsilon. Good. I'm proud of you. Obi-Wan has taught you well. There must be some non-epsilon cycle. How many get that? Because if it's epsilons around the cycle, all you're doing is getting more and more epsilons, and you're not increasing the size of the string. You're not getting any new strings. And the language may not be infinite. It may be infinite for some other cycle, but not this cycle. So you got to find a cycle, a non-epsilon cycle. Okay, so that's the 4th condition. Okay, but still, you can do this, and you can do this relatively quickly. Quadratic time will certainly suffice, and if you're clever, you can do it in less quadratic time. Anyway, polynomial time will answer this question. But even if it was not answered in polynomial time, and you have to look at all possible cycles in exponential time, that's still decidable, right? We're talking about decidability right now. We're not talking about efficiency. Later in the course, we'll talk more about efficiency, not just decidability. Now, right now, we're just wondering if it's possible or not possible. And there's a good reason why we have to wonder, because we already saw problems which were not possible, like the halting problem, not possible to solve algorithmically. So you can't take it for granted that everything is doable as long as you can state it. It's not true. Some things are very easily to state and very precise, yet there's no algorithm in the universe for them. All right, let's try another one. I give you 2 finite automata, M1 and M2, and ask you, is their languages the same language? Do they both have the same, recognize the same language? How do you do that one? Let me tell you how you don't do this one. Iterate over all possible strings, and for each string, run both machines on it and make sure they agree. What's the problem with this non-algorithm? Yeah, it's like infinite long to execute, and then it'll never get the answer because there's no end to an infinity. So it's not an algorithm. It's just some words I uttered. So that's not how you do it, right? But so how do you do it? Tell if both machines accept the exact same language. There's a number of ways you can do this. I agree it's not trivial, so if it was trivial, I wouldn't be insulting your intelligence by asking you this question, right? a bunch of smart graduate students like yourselves. Yeah.
We convert it to a DFA and minimize it, and therefore check if those two DFAs are the same. Because it's like
Okay, so let's say they're already DFAs. So you don't have to worry about non-determinism. So how do you compare these two DFAs to make sure they accept the exact same language as the other?
you know that there is existence of one minimal DFA.
So you can minimize both DFAs and then see if it's the same DFA. What do you guys say to that? It's an interesting technique. Right? Minimize the two DFAs and have the same number of states and then compare them to make sure they're the same DFA. What's
They don't have to be the same states.
Yeah. So what if you get two separate, different DFAs, the same size, but different structures, different loops, different arcs? They both accept the same language, but they're not the same DFA. How many say that can happen? Yeah, that can happen. If you write a piece of code and somehow write the minimal piece of code, the smallest number of characters or lines to do the job, like prime numbers or whatever it is you're trying to do, you write the smallest piece of code possible. Let's say you were able to prove that's the smallest piece of code. Never mind how, but does that mean that there's no other program with the exact same number of characters that does the exact same job, but it's a different program? How many say that could happen? Different program, same size. Yeah, of course it can happen. So the minimum size program has the unique minimum size, but it's not the unique program for that size. That can happen. So it's a nice thing to try. It's a good try, but that doesn't address that issue of two machines, both the same small size, different structures. So now they won't look like the same machine, but they will do the same job. So how do you figure that out now? So what else can you do? Yeah.
Take the intersection as a union.
Okay. So if you take the difference between two machines and you take the other difference between the two machines, in other words, one difference will be this region here, one difference will be this region here.
And X1.
What do you know about this difference and that difference if the two languages are the same language? Both differences will be what? Type error? Empty set, yeah. Just making sure. Yeah, but you're right. It's the 0 for sets, which is the empty set. So if both differences are the empty set, that's true if and only if the two languages are the same. How many believe that? Yeah. So these two sets are the same if and only if both differences are empty. Then the two sets coincide. If one of the differences is empty, is that enough to conclude they're the same set? No, because one could be a subset, a proper subset of the other. And you subtract the big one from the small one, it'll be empty. But if you subtract the small one from the big one, it won't be empty. Okay, how many understand that? So you have to do it both ways. So do both subtractions, make sure both subtractions are empty. Now, how do you know if this subtraction is empty and this subtraction is empty? You have two machines. You don't even have the languages. So what do you do now? And we're not done. Explain how do you exploit this property of set equality if and only if the two differences pairwise are both empty. How do you exploit that into an algorithm? It's not an algorithm. Right now it's just a property of sets. Cross-product construction, right? Or construct the machine that accepts the difference and the other machine accepts the other difference using the cross-product construction. And what do you do with these two new machines for one difference and the other difference? Now, this part is easy. It's a hint. So you want to make sure that both machines accept nothing. And how do you accomplish that? Graph reachability. It's the answer to the first one. Right? Good. Using a subroutine is a good thing in computer science, right? In fact, that's what computer science is about. Imagine if you couldn't use subroutines. What would computer science look like? Every time you wanted to add two numbers together, multiply two numbers together, you'd have to implement the machine code that does these operations. It'd be tedious. Computers will be useless, basically. So whenever you can, use other solutions as black boxes, as subroutines. In mathematics, what's the mathematics equivalent of computer science subroutines? In mathematics, there's a name for them in terms of proving things. Lemmas. Thank you. They're called lemmas. Subroutines are called lemmas in theorems. Right? The theorem is the program as subroutines are dilemmas. Good. So construct the two machines for the two differences using the cross-product construction from 12 slides ago or so. Both different machines, and then feed both machines to this algorithm, and then you'll know if the language of the two machines are the same. Any questions about that? So this was progressively more intricate in terms of deciding these properties, and there's a whole bunch of other properties you can decide that are even more complicated than that. Any questions or comments on any of this? Thoughts? Here I'm saying what I told you earlier, that finding the smallest equivalent regular expression, it is decidable, but it turns out it's p-space complete. So it's worse than NP-complete. To answer the question earlier, it's actually p-space. You can prove it's p-space complete. Now, why is it decidable? How would you find the smallest regular expression if you can take all the time you want it? Exponential time.
Convert the NFA to a DFA, minimize the DFA, use that and convert it to a regular expression.
Okay, but how do you know it's the minimum? It won't necessarily be the minimum, because when you convert the NFA to a DFA, you get exponential explosion, right? And then when you minimize that, yeah, you can minimize that, but it won't necessarily be the smallest regular expression that comes out of this process, because you blew it up to begin with, and that could have hurt the size. But it's a good try. What else can you do? Let's say brute force. Just do it brute force. Don't try to be efficient about it, because we don't know how to be efficient about it. If we knew that p space will be equal to p, and then p is equal to np will be a corollary of that, and you'd get $1 million prize from the Clay Institute of Mathematics for solving this open problem. Who wants to be a millionaire, right? So don't try to do it efficiently. Just do it inefficiently. Brute force. How do you find the smallest regular expression equivalent to the one I give you? Brute force.
All possible regular expressions.
Yes. Generate all possible regular expressions smaller than it. All of them. And for each one that you generate, you do what? Check. Good. I like that. One word answer. Now, somebody expand that one word into a sentence. How do you check two regular expressions for equivalence? Again, don't try to be efficient. Just do it any old way. You have a regular expression, another regular expression. How do you tell me if they denote the same language, if they're equivalent?
You know the language is represented by the vector. So L1 minus L2 and L2.
Yeah. So how do you know the languages, and how do you compare the languages, the two regular expressions?
Convert to the machines.
Yes. Convert them to machines. Then take the machines and do what? Do this. Subroutine. Right? Lemma. So now you see we're building on top of previous results very heavily. And that's a brute force approach. Why? How many regular expressions are there that are smaller than a given regular expression? Polynomial, exponential, linear, quadratic, exponential. But you can try them all. Right? How do you generate all regular expressions, by the way, smaller than a regular expression? How can you be sure you got them all?
Scale through the powerset.
Yeah, parse them. Generate all strings in sigma star smaller than the string of the irregular expression. See which ones are actual regular expressions by sending them to a compiler parser. And if a compiler parser doesn't complain, it's a valid regular expression. It's easy. I mean, a parser by itself has some complexity to it and some non-trivial kind of trickery to it, but you can do this. The point is it's decidable. So see, it wasn't even obvious it's decidable. It took quite some doing to actually come up with even an inefficient algorithm for it, never mind an efficient one that would solve an open problem. Okay. Now, we already mentioned that minimizing Turing machines or even code, undecidable. And I'll let you, ponder why, and later we'll get back to why that's undecidable. So minimizing things gets harder and harder as they grow in complexity and generality. Right. Regular expressions can't represent arbitrary languages, just the regular languages. And even that it's not obviously it's efficient to do, but we do know it's decidable. Turing machines, we know for sure it's undecidable to come up with the smallest Turing machine that does a job. Same for code. And actually same for push-down automata even, for context-free languages. Right. So now in the book, we're going to enter context-free languages next time, but right now you have plenty of information to completely finish homework number 2, and soon enough we'll post homework number 3. Again, these are just a few problems here and there that encourage you to keep working on it on a daily and a weekly basis. How many of you are working in groups? Okay, a few of you. I want more of you to be involved in groups. Find other people that are in a class, work in groups, meet a couple times a week. How many are coming to the problem-solving sessions on Saturdays? Good, a bunch of you. Keep doing that. If nothing else, you get free pizza on me, my gift to you. Because it's a good thing to come to these sessions. I'm putting my money literally where my mouth is, or where your mouth is. You know, pizza, free pizza. So keep solving problems, and we'll see you around.